Moving on to the calculations involved in the unconfined compression test. Here are the specifications of the cylinder we used. The height was 3 inches or 76.2 millimeters. The dia was 1.5 inches. The area was 1.77 inches or inch square or 1140 millimeters square. And this is the volume. The proving ring constant was 9.03 newtons per division for this device, and the least count of the deformation dial gauge is 0.01 millimeters per division. The weight of the specimen is over here, and the moisture content is this. Now over here is the for our calculations. First is the deformation dial gauge readings and the load dial gauge readings. These I noted along as the uh, test progressed, with each intervals of 10 for the deformation dial gauge and the corresponding load dial gauge reading up until it reached its peak value, and then it started to drop after that. So this was when our test ended, when I turned off the machine, and then when I started bringing it down. So what we do is, to determine the deformation length in millimeters, we multiply it with the least count that's given over here. So what I did is that I multiplied B12 with H7. H7 is where the deformation dial gauge least count is given. So I multiplied that with that. The dollar signs indicate that even as I drag this down, uh, this cell will remain constant. It will not be disturbed, and this value will constantly be multiplied with all the values down here. That's what the dollar signs indicate. Okay, so next is the percentage axial strain. So strain, as you know, is change in length over the original length. So delta L divided by the original height of our specimen, which was 76.2. So what we do is we divide this with E3. E3 is where our original height is. So we divide this with E3, and then we multiply with 100, and then we just drag it down, and this is our percentage strain. I mentioned in the video that our test goes up until the maximum load is achieved for 3 consecutive intervals of the dial gauge, multiples of 10, or until it starts coming backwards, or if we reach percentage strain equal to 15%. Currently, we've only reached 3%, but it already failed at that point, so that's why we stopped our test. But if it kept on going, if it kept on raising like 47, 48, up to 100 or whatever value, we would still we would note down that how much it would raise until this value, the percentage strain, reached 15%, and at 15% we would stop the test. Okay, so next is our area correction factor. You might remember in direct shear test we also performed an area correction. However, area correction was done with using what do you call it? Uh, in direct shear test, the area correction factor resulted in the area reducing because the contact area of the soil grains was reducing as the upper shear box moved beyond the lower shear box. However, in the unconfined compression test, we have a different area correction factor. We calculate it as such that, as you can see over here, this is our original cylinder, its length L, its area A naught. So our volume is equal to L into A naught. However, once the sample starts to be compressed, when the cylinder is compressed, then then our length reduces and our area slightly starts to expand a bit because it's stretched out once it's squeezed. So we have a new area and we have a new length. However, our volume will remain the same. So our new length is L minus delta L, and this is our new area. So if we just adjust the values in this formula, we can get the new value for the corrected area, and that is given over here. This corrected area is equal to the original area divided by 1 minus strain. Now this is unit strain, it's not percentage strain. So what we do over here is we just for the correction factor, we do 1 minus, this is percentage strain, we just divide this value by 100. So as you can see over here, 1 minus E12 divided. So as you can see over here, I'm minusing 1 minus unit strain, and then I'm dragging this formula down. So this is our correction factor. Then we just have to divide our original area by these correction factors, and we will be given our new corrected areas. And as you can see over here, the area is slightly increasing with each uh, turn of the dial gauge over here. Our axial load we can calculate pretty straightforward. Just multiply the value of our load dial gauge reading with the proving ring constant, and we have our load reading in newtons. And then stress is dividing, our compressive stress is obtained by dividing our load dial gauge value, our load value with the corrected area, and that's Newton per millimeter square, so that's megapascal. So we multiply that with 1000 to get kilopascal. We drag this down and we get this data series over here. Now you can see I've highlighted 353. 353 is our peak stress value over here. As you can see, beyond that it starts to decrease. So there are two graphs that we can draw for this. One is our stress versus axial strain. So we just get the values of our stress and our axial strain, strain on the x-axis, stress on the y-axis, and we get this. The next we have to do is using the same Mohr-Coulomb failure envelope, we have to draw a Mohr circle. So how we draw a Mohr circle, how we draw this. Now this is our circle's diameter. This is our compressive strength, or rather it's our unconfined compressive strength. So we have to draw this to determine what our undrained cohesive strength is, or our undrained strength of the soil is, or our cohesion value of the soil is. So how we do this, we have to make these columns. So now this is our diameter. So if we divide it by 2 is equal to this divided by 2. Okay. So this is our radius. Now first what we have to do, because this is a semicircle, we have to make down a series of 0 to 180. This is degrees, and then we have to convert those into radians. As you can see, just multiply with pi and divide by 180. We have this in radians. We also have to drag this all the way down to 180. Now for our x value, what we do is x is equal to r, our radius, plus r cos theta, where theta is in radians. So we just apply this formula over here. You can see I-35 is this cell, the peak value, So I've just divided I35 by 2, that's R, plus again R into cos and the value in radians. You drag this down, that is your x-axis values for this circle. For the y-axis, what we do is r sine theta. So this cell divided by 2, 353.342 divided by 2 into sine of the value in radians. You drag this down, you will have your value for the y-axis. Now when you plot this, and when you plot this chart, so now what we can do, we have our radius, our circle over here. So now we also have to plot a tangent that extends from and touches the apex of the circle. So how we do this is 176.671 Okay, so we just have to add another data series over here. The x values will be this, our y values will be this, and when we plot this, this tangent is drawn over here. Now, similar to your direct shear test, this is also you achieved a line in your Mohr column graph, and that line, it's where it bisected the x-axis, the y-axis, that was your what do you call it, intercept, or the value of c, and the slope was equal to tan phi. So over here you can see that your slope is negligible because it's a straight line, 176.671. So your shear stress is equal to just the value of your cohesion, because there is no angle of internal friction in this that's playing a factor in this. So your tan phi is equal to 0, because phi is equal to 0 in this. So your shear stress is just equal to the value of your cohesion, which is half the value of your unconfined compressive strength. And that's pretty much all there is to your calculations in this test.